Okay, here's part 2 of the limits. We're going to be looking at this function here. It's just a random function without any closed form notation. We can't write it out in terms of x, but we're going to be looking at the different limits at different places. We'll start with x equals -1. So at x equals -1, you can see on this function that it's defined here to be 3. So f of -1 is 3. It is not defined here at this open circle. That's what the hole means there. So now what we can do is find the limit at x equals 1. So we'll start with the right-hand limit. So the limit as x approaches -1 from the right of f of x will be this. So we'll start somewhere to the right of -1, say here, and we'll look at the function. So we see if we follow this function here as we approach from the right, it kind of veers off down to -infinity. So let's start a little bit closer. So if we pick a value here, then on our function we're way down here. So as we move to the right, our function moves back up above the x-axis, and we approach what looks to be 2 here. So the limit as we approach from the right, approach -1 from the right, is 2. So if we find the left-hand limit, we pick an x to the left of -1, and we approach -1 from the left. So as we pick an x here, we find our corresponding f of x value here. And as we move to the right, we see that as we approach -1, our function approaches 2 again. So that means that our right-hand limit equals 2 and our left-hand limit equals 2, which means that the limit as x approaches -1 of f of x exists, and it's equal to 2. So now let's look at a different one. Let's look at x equals 1. So at x equals 1, our function is defined to be 1. So f of 1 is 1. So again, this time we'll start with the right-hand limit. So if we pick an x to the right of 1, so we want to find the limit as x approaches 1 from the right of f of x. So we'll start somewhere to the right of 1. So we'll pick this x here, find our corresponding f of x value here, and as we move to the right, you can see our function decreases and it approaches 1. So now let's find the left-hand limit. So the limit as x approaches 1 from the left of f of x. So we'll pick an x value here to the left of 1, and we'll approach 1. And as we do that, our function increases and it approaches 2. So it approaches this empty circle, 2. So we can see that the limit as x approaches 1 from the left of f of x is 2, and the limit as we approach 1 from the right is 1. So since they are not equal, the limit as x approaches 1 of f of x does not exist. DNE for does not exist. So let's try another. Let's try one for x equals -4. So f of -4, we can see, is just defined to be 0. It's on the x-axis. And if we find, we can tell just by looking at it that it's we have 2 connected sides of this graph. So we'll just look at the limit as x approaches -4 of f of x. We can still look from the left and from the right, though. We can still approach -4 from the left, and we see that we get 0. And we can approach from the right, and we can still see that as x approaches -4 from the right, we get 0. So this limit exists, and it's 0. Okay, so now our last one here, we'll check our last couple of here. Okay, so the limit as x approaches 0 of f of x, so we want to find this. Now, we don't have to write it down every time, but we can say that the limit as x approaches 0 from the right of f of x, we can find this value first. So as we approach 0 from the right, so we'll look to the right, we'll pick an x value again, find our corresponding f of x, approach from the right, and we see our function decreases sharply and approaches -infinity. We look from the left, the limit as x approaches 0 from the left of f of x. We'll look at an x value to the left and continue towards 0 and find that as we approach 0, the function decreases and goes towards negative infinity. So the left-hand limit matches the right-hand limit, so the limit as x approaches 0 of f of x exists, and it's equal to negative infinity. So now the last one, the limit as x approaches 3 from the right of f of x. So now we'll look here to the right of 3, and as we approach from the right, f of x shoots off into infinity. So we approach from the right, this goes to infinity. So now that we've found that, let's look at some of the limit laws, some of the things that can help you find limits algebraically. So that what we just did was a good way to find things using the graph of a function. But if we want to do things without, we want to find limits without doing that, we need some rules to do that. And you can take a second to pause the video here and look at these limit laws. Once you're done with that, there's another page here. You can take a look at these limit laws. So the important ones will be the sum rule, the difference rule, and the product rule. We'll use that a lot, as well as the quotient rule. Okay. So now we can find a few of these limits algebraically. Now, for any polynomial, you find any limit. Well, the thing about polynomials is that they are continuous at every number in their domain. And their domain is all real numbers. So if you plug in any number, you can just find its limit. So the limit as x approaches a, well, first we can split this up. So we can say the limit as x approaches a of x cubed plus the limit as x approaches a of 5x squared plus the limit as x approaches a of negative 2. So this will be equal to that. And we can find each of these individually. So the limit as x approaches a of x cubed is just a cubed. The limit as x approaches a of 5x squared is 5 times a squared. Plus the limit as x approaches a of negative 2. For a constant function, it's just negative 2. So we can simplify it a bit. And we just get that the limit is equal to a cubed plus 5a squared minus 2. So this is just for general a. So you can plug in any number for a and you can get the limit at that number. So if we try b here, the limit as x approaches negative 5 of the square root of 7x squared minus 2 will just be equal to the square roots of the limit. You can think of it this way. So you can bring the limit in, you can leave it out, but the main result will just be plugging in negative 5 into x. So we can say that this is equal to, this limit is equal to 7 times negative 5 squared minus 2. So we'll just simplify this. So this is 7 times 25 minus 2, which is the square root of 175 minus 2, which is equal to the square root of 173. Now the reason we can do these things, we can split these up, is this comes from the delta, this is not delta, the delta epsilon proofs. So this comes from the precise definition of limits. So these are very hard, but what you do is you prove certain things about just the function x and just similar polynomials, and you use algebra on these to create some of these other types of functions. So you start with simple things and you build up from there so that you can just eventually just plug in. But let's see some more examples. Another example. So see, this is here, we want to evaluate the limit as x approaches 1 of x squared minus 2x plus 1 over x squared minus x. But this is a rational function. We can think of it, though, as a polynomial divided by a polynomial. And as we saw before, if you want to evaluate a limit of a polynomial by just plugging in the number that you want to find the limit at. But the only issue here is that if you plug in, just on the side here, if you plug in 1, you get 1 squared minus 2 times 1 plus 1 over 1 squared minus 1. So what you get in the top is 1 minus 2, or rather 1 plus 1, which is 2, minus 2. So you get 0 on the top, and then 1 minus 1 on the bottom. So you get 0 over 0, which is an indeterminate form. But the good thing about an indeterminate form is that it suggests that you can simplify it a bit. So let's just see what we can do with this limit as x approaches 1. So in the top, we can see that it's factorable. We can factor this quadratic into x minus 1 squared. And the bottom, we can factor out an x. So this is x times x minus 1. And now we see that some of the x's cancel here, the x minus 1s. So x minus 1 squared over x minus 1 cancels with 1. So we're left with just x minus 1 over x. Now if we plug in 1, we see we get, well, 1 minus 1 in the top would give you 0, and in the bottom we get 1. So that's much better. So now, just as an aside, we plug in 1, we get 0 over 1, which is something we can handle. That's just 0. So let's go ahead and just plug those in. So 1 minus 1 over 1 is equal to 0 over 1, which is equal to 0. So the limit of this function as x approaches 1 is just 0.